Marissa, I'm sorry I missed the lab.
Okay, can you make it up at another lab session during this time?
During...
Like Tuesday, Thursday?
Aren't you going to be doing a separate lab though during that time?
Yeah, but then you could run your own lab separately.
Oh, yeah, I can do that.
Okay, yeah, so whichever one works for your schedule.
Yeah. What time is the Thursday one?
1:30 to 4:20.
Oh, no, I can't, dang.
Okay, then we'll just have to try to squeeze it in on Friday. Which I think you should be able to make it up because it's a pretty short lab.
I mean, yeah, it'll work out.
Yeah, and then I think that's it.
Yeah, that's the only thing I missed.
Okay.
Because Friday was wild.
Yeah.
Yeah. You okay?
Yeah.
Cool. Sorry about that. Are you about to start?
I'm just trying to use the bathroom.
Oh, you can, sorry.
Like these first ones? That was one of the rest of them? That's where the whole give us all the questions. Like this stuff? Dude, oh my gosh. You got. I'm like so unsure. This one right here, he showed us that example. Because he did it, and he was on engineering, page 1 and 6. It was just like, that was just the vector question. I think the calculus. Yeah. Which is just the bottom. Which one? I'm not excited. Because it's physics 201 and 211. Well, I don't know how to differentiate. It's a concurrent course, so you can take it and do it. You know? I asked him, I was like, I'm good to take both these courses, right? Because it's a co-requisite. And he's like, yeah, you know, like you don't get into the deep stuff until you're doing your calculus final. Went straight into it. I was like, that's my mind. Dude, I've been awake since midnight. Doing that. I did the math last night. I gotta take 17 credits this term, 20 next term, and 20 the spring term. But then I chill on the summer until I come back to 10. I'm so confused. You guys have to take different equations? Man, if I was on my doctor, I'm still alive, why not? You're still alive. I'll talk to you later. Last night, I like 2 in the morning, I was doing the math on the first night. You do some math, just do another year. Like whenever you're at not working too much. No, did you write the pace for everything? Doing that on top of working. Fridays I'm helping my brother do the property that is. But I got like drill. I got drill this weekend, so I'm gonna show to Country Line on Thursday. Oh yeah. As soon as it gets out, I'm driving straight to the airport. So I'm not gonna have time to do that. I'm trying to break out. I haven't had acne. I never had acne. Yeah, I'm losing my hair.
Okay.
By week 11, I was I'm involved in these things. No. An example of a musical process. That's like me. Is he covering one?
All right, let's go ahead and get started today. So any questions before we get going? And so of course, right, if you need a couple of days on the homework, that's fine. I know we've already fallen behind schedule. So, you know, just focus on getting the homework complete. So let's look at our chapter, unless, like I said, there's any other questions. And so now we're diving into chapter 2, so really getting into, well, what is chemistry? And so, of course, your book starts off, again, right, matter is composed of particles. And so these particles, right, they can appear solid, they can be the air with the tiny particles that we cannot see. And then we'll even look into, of course, our subatomic particles, such as our neutrons, protons, and electrons, of course, make up our atom, and we'll look at that. And so we'll also look at how to represent these molecules. And so here is kind of our ball filling model with oxygen shown in red and hydrogen is in white. And so, of course, we'll start learning, right, physical properties. How can we predict them? What does it mean if something's a solid, liquid, or gas at these different temperatures? How do we work with it? How do we add it as a reagent? And of course, right, chemistry seeks to understand matter and create new matter, play with different molecules, right, make new compounds and do cool things. And so, of course, we have our atoms, which are just our fundamental building block. And so atoms are, right, any element on your periodic table. So you can link those two together. And then our molecules are going to be two or more, right, different atoms.
So I had a question about that, because I did the chapter 2 quiz, and one of the questions I got confused about, in the book it says that some elements are naturally, I forgot the word for it, but it's two of them, like oxygen.
Yeah, diatomic.
Diatonic, are those still considered molecules, even though they're the same?
So those would be considered elements.
Okay.
And so we'll get there, so we're like almost right there. So that is why I made the distinction of molecules being two or more different atoms. Yeah. Yeah, so hold your thoughts for like 10 seconds. You're jumping ahead of my lecture. So, right, we can go CO. And so again, right, an element is a substance that cannot be chemically broken down into a simpler substance. And so, right, we're saying chemically. So obviously we can talk about nuclear reactions, and then we can start changing the identity of atoms. We're not focusing on that right now. We're just, again, looking at fundamental atoms. And so a compound, like I said, the key point here is that it's in fixed, definite proportions. All right, so now let's jump down to what everybody was getting all excited about right away. So we had diatomic molecules, so let's just at least define that. So we're saying, and so let's say that it's an atom that exists as a pair, and I'm going to use this term, so in its elemental state. And all that means is if we find it, right, alone as an element, so, right, just one of its kind in the environment, it's going to be a diatomic. So it's going to be paired with itself. And so there are 7 of them. So who can list them? Do we know them?
Oxygen, nitrogen.
So oxygen, nitrogen, hydrogen.
Is it helium? No.
Yeah.
Isn't it like a Brinkelhoff? Like there's bromine, or bromine, there's iodine, there's chlorine, oxygen, hydrogen, fluorine, I believe?
Yeah, so now we're starting to get to the pattern, so let's highlight them if we need to. So we have hydrogen is by itself, that's the only one you really need to remember. And then they make a little, it looks like a 7, but it's only 6 elements in the 7. And so yeah, like he was saying, all are halogens, so fluorine, chlorine, bromine, and iodine are all diatomics.
Is that your acetane as well?
I'm not sure about this one. Yeah, I mean, it's not the common diatomics. That's a weird molecule. So again, write these down. So you want to know them or have them highlighted on your periodic table, noted in some fashion. Okay, those are our diatomics. And then another example was brought up. So let me finish writing our 7 diatomics out. So I'm missing our halogens, so chlorine, fluorine, bromine, and iodine. So 1, 2, 3, 4, 5, 6, 7. Okay, got them all. And then, so what are allotropes? We just named an example.
Would oxygen also be considered another term like triatomic? Because the ozone layer is O3.
Yeah, so it can also be O3, and so that might fall under this definition. So what's an allotrope? Or other examples of allotropes? What was your example earlier?
Carbon.
Carbon, right? So carbon is always our classic allotrope example that we start with. And so what forms can carbon be in?
In the form of diamonds.
So diamond, what else?
Like
So graphene or graphite. So graphene, graphite. Other structures for carbon.
there's like a spherical structure. I forget what it's called.
Spherical structure, yeah, so C60. And so what distinguishes them? So I'll pull up the Wikipedia page. Wikipedia is always good for science, and so here's the allotropes that we had named. So A is diamond, so notice, right, the repeating tetrahedral pattern. B is graphite, so graphite has sheets, so it can shear off, and that's what you write with. I'm not familiar with this structure, but then, so D is the buckyball, so that was pretty famous. And of course, the buckyball led to carbon nanotubes, so that's H down here, so it kind of led to a whole new field. And then, of course, right, there's other structures as well. And so what's the difference between these? We still don't have a definition for allotrope, but yeah.
I mean, it seems to be carbon rearranged in different but similar shapes. So, like, you kind of have a plane of carbons put together in flat sheets versus, like, a sphere versus, like, sort of intermingled with each other.
Yep.
It's all about arrangement.
So then there's our definition. So write different geometrical arrangements. Of the same atom. And so again, right, this is still an element, so it doesn't matter whether carbon is a diamond, a graphene, right, a buckyball, still an element, still carbon. And so let's at least talk about a few common allotropes. Obviously not an exhaustive list, but just go over kind of a few famous ones, if I could spell phosphorus for a second. So phosphorus, anybody heard of phosphorus allotropes? What are they famous for?
There's white phosphorus and red phosphorus. Like red phosphorus is on the tip of a match, and then white phosphorus is like banned by international law.
Banned by international law, but still used. But yes, so white phosphorus, so when it's used in like military applications, they put it in a carbon disulfide, which is just like CO. So now I'm getting too excited already.
Is phosphorus just a P on the table?
Yeah, but we'll talk about, so, sorry, I got too excited already. So this is carbon disulfide, so it's just like CO, except with sulfurs. So now you're starting to already see patterns. But yeah, so they dissolve or like put it in a solution of carbon disulfide and any other nasty stuff. And of course, as soon as that white phosphorus is exposed to air, it's pretty reactive. And so, you know, goes kablooey, is obviously pretty toxic. So this was lovely, right? So you can get phossy jaw, which just means like eventually your phosphorus or all the calcium in your face starts dissolving off because it's reacting with all the phosphorus. Lovely stuff. So that's, again, why it's super toxic, among other things. So that's white phosphorus. And so, yes, phosphorus is just P on the periodic table, but, right, you might see this P4, or, again, signifying this allotrope. And so we can look at other forms. So, of course, there's our red phosphorus. And then also violet phosphorus. So, again, just different structures. And so other allotropes, I'll just put kind of P4, right? We can write white, red, violet phosphorus. So another one that can confuse people is sulfur. It's not as common, but it probably does have allotropes. Like I said, I'm not going over all the allotropes, right? We could ask, so allotropes of silicon. So I don't know if it's that common. Yeah, so probably not as some. So there's some apparently 2D structures. I wish it actually had, there we go, structure. So yeah, some allotropes, but like I said, just kind of the common ones. So let's look at sulfur. Sometimes you see sulfur written funny. And so sometimes you see sulfur written as S8, and so that just reflects its common crystal structure shape here, so it makes this weird 8-membered S ring, sulfur ring, so kind of strange. So let's keep looking at our matter here. And so then your book kind of goes into it. So, right, we, of course, classify our matter by its state. So we have, of course, right, solid, liquid, gas. And so we may know that our solid particles are, of course, packed extremely tightly and are fixed in place. But of course, right, there's still molecular motion, so you want to think about that, right? They're still vibrating and, you know, wagging, shifting. There's still electrons running around very rapidly, so there's still a lot of movement here.
I have one more question.
Yeah, so you're starting to already think about the intermolecular forces, so that's, yeah, it's further down. Yeah, but we can still think about it, right? So solid matter, you can think about ice. It's packed in a crystal structure, so obviously it's cold. And then, of course, we start adding energy, usually in the form of heat. And so, right, that starts just moving them more, right? So again, it's not like they were just solid, frozen. They're moving. And you give them more energy, so they're moving more and more. And so, right, as they're moving more and more, and you can think about that ice melting, so now it's becoming a liquid, right, as those particles have enough energy to kind of slide past one another. Yeah.
So there are allotropes in solid molecules. Are there maybe allotropes with like behavior within liquids, or?
I mean, allotropes just refers to like a solid structure more. And so I'm going to put our key term here. Again, we'll revisit this much later. But, right, we're breaking our intermolecular forces, right? We're not breaking bonds. We're not destroying compounds or anything when we heat them. We're just disturbing those intermolecular forces that keep them kind of bound together. And then we start, again, changing the states of matter. And so then, right, we start adding more energy. Again, thinking about steam, because these intermolecular forces, right, it'll all go back to, well, why is something a gas? Why is something a solid? Why is something, you know, a liquid? So we'll keep revisiting that. But again, so now we take our water, we're adding even more energy. So now those molecules, right, they don't just sit in the water. Now they can actually fly out, right, against the atmospheric pressure, which is something we'll talk about, and become gas. Yeah.
Do all elements have all three of these states, or are there some that don't?
Yeah, so they all exist, right? Theoretically, it's just, again, what we can observe. So that's why I was like referring to water, since we've seen that probably at all three states, right? But not many people have like melted gold, right? That has a pretty high melting point possible, but, you know, not reasonable. Same thing with hydrogen. You know, later we'll talk about solid hydrogen. So solid hydrogen exists, you know, in the stars. So yes, everything has.
Is there liquid carbon?
I mean, I'm sure at a certain state, yes. Have I worked with liquid carbon? No. And I've worked with a lot of things. But. And so now, blah, 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 kind of the words to match that. So like we're saying, as we give them more energy, then they can change states of matter. And again, right, you can identify classic examples. So ice is a good solid. Of course, aluminum, right, big piece of metal. So that's what a solid metal looks like. Diamond, again, thinking of our carbon repeating network in our tetrahedral structure. And so again, liquid, the key definition is a fixed volume. So you know that, right? You can transfer your liquid over from container to container. And of course, not a fixed shape. And so liquids have the ability to flow, of course, and right, water, alcohol, so that could be ethanol, right, isopropanol, any alcohol, gasoline, so gasoline is really just a mixture of hydrocarbons. So, right, you can put on there octane, etc. And then again, gas. So gas, the key word that we like to use to describe a gas is that they are compressible, right? So we could compress a gas all the way back down to a liquid. You know, you've probably seen those liquid nitrogen tanks at like the dealership for filling up cars, right? They have a huge tank. So it's liquid in there, but then of course it comes out of the regulator as a gas, so at the appropriate pressure. Yeah.
In what situation would you fill your car with liquid nitrogen?
No, you use it for the tires.
Oh, okay.
Yeah, so it's best to fill your tires with nitrogen. So yeah, that's why they have that there. And so again, compressible. So we can compress them, right? They take up all the space. We could pop a balloon, and then the gas would spread throughout the room. And so I'll bring some balloons of gas on Thursday for some fun. All right, so then we get to how do we classify matter, which is also getting into really how do we separate it, because that's the true heart of chemistry. And right, I'll give you a quote from one of my mentors, right? My 3-year-old can mix stuff together, but they can't separate it, right? So that's kind of the idea. Anybody can mix some reagents together, right? You can throw it in the pot, but then what? It doesn't mean anything if you can't separate it out and get out a pure compound. And so, of course, to kind of separate stuff, well, we have to determine our roadmap of even what are we working with. And so we have our matter here. And so kind of the first question is it one type of particle? So really it's asking, is it an element or is it a compound? So let's kind of go through. So element, right, we said obviously found on the periodic table. So let's kind of put that found on table. And then obviously, right, don't forget our diatomics and allotropes. And now what makes a compound?
It's multiple substances put into one.
So multiple substances put into one, but then we need, because that could be a mixture, right?
It has to be bonded with chemical bonds.
So it has to be bonded. What are other good definitions?
It's a compound is recognized as a fixed number and fixed proportions.
So fixed proportions, so I'll reword that as defined chemical formula, but yeah, that's the idea, and the idea that we're getting to in the chapter is kind of defined proportions, defined chemical formula. Did you have?
Two or more substances combine chemically with distinct properties.
So 2 or more substances, that was a good definition. So combined chemically and defined chemical formula. So I'm mainly looking for the defined chemical formula, but it's still good to kind of make that distinction, right? So they're bonded chemically. We have a chemical formula, right? We can always say that's true, and we can characterize it, crystallize it. So, right, sodium chloride, aspirin. What are some other compounds?
Ammonia.
Ammonia. Carbon dioxide.
Our air, like what we breathe in.
Ooh, so air, what's air? So chat said sugar. What's air though?
More of a amalgamation.
Yeah, it's a mixture. So air, let's put air under our homogeneous mixture. Right, so air, what's in air? So obviously a little bit of oxygen. What else is in there? So nitrogen, so right, it's primarily nitrogen, like 78% nitrogen.
Hydrogen.
And so then, right, trace of hydrogen, trace CO, right, other trace gases. So mixture, and right, homogeneous mixture, right, there's no one part of the room that has all the oxygen that you go breathe in, right, it's all evenly distributed. All right, excellent. Back to compounds, other compounds, any favorite compounds?
Carbon monoxide count too?
Carbon monoxide, so CO, yes, defined chemical formula. So glucose, so we like our sugars.
Proteins or amino acids.
So amino acids, so starting to get bigger, but right, still, so I'll kind of put them, so amino acids.
DNA.
So I probably wouldn't put DNA necessarily in like compounds. That's That's actually a good question, how to classify it. Because it is kind of defined, but right, it's probably really wouldn't classify DNA like we would, yeah.
Would like a benzene ring that's found like in like phytochemicals count as
Oh, like benzene itself would, yeah.
okay, yeah.
So you have to, yeah, so someone's asking about tissues. So once you start getting to like more complex biological structures, so that would be like more, yeah, kind of mixtures or just like proteins, so they don't quite fit.
Would DNA be better classified as like each of the pieces individually? Kind of, you could define some of them as compounds, but putting them together is its own separate thing.
Yeah, that's why I didn't want to get into like classifying, because it's not like our typical
Yeah.
separation, because, right, I'm thinking back to chemical separation, right? So DNA, you would use a different technique, right? Obviously, you do your DNA enzymes and all that, so it's kind of different.
Can you scroll up so I can take a picture of the chart, please?
And then the notes are available online, so I do have the live link going. Yeah.
What about like uranium hexafluoride?
So that would be a compound. Yeah, so define chemical formula. So let me write uranium.
So a compound is anything that can be written in elemental form.
Pretty much. That's where like the DNA thing gets tricky, right? Because you can still write it out. So we could, write it out with the corresponding amino acids, blah, blah, blah. So like, still separatable. So I think that's kind of the distinction is like you can separate DNA. So we could kind of call it a compound, but I don't want to get too far down the biological rabbit hole on that. And so what I'm, again, more thinking of is mixtures. So, right, your nasty chemical mixture, potentially, that you have to mix or separate, right? It has some salts byproduct. Somewhere in there is your organic. And so looking at your mixture and kind of how to approach it, you might want to ask yourself, right, is it heterogeneous or is it homogeneous? So what does heterogeneous mean?
It's not necessarily purely mixed, or it's mixed on macro scale as opposed to dissolving.
So, sorry, I didn't quite follow. What did you say again?
So it's mixed together, but it's mixed as particles. For example, wet sand. For example, here you've got entire solid pieces within a liquid. They don't share the same state, and they're not separated molecularly in the liquid or like homogeneously.
So like distinct regions.
I was gonna say, it's not that a uniform mixture. It's not, it's just not as mixed well.
So maybe not mixed well, or it could be that you have like big particles like sticking out of it that are like just insoluble. So that's also kind of what we're thinking of. So right, with heterogeneous, so we have distinct regions. So basically not uniform throughout. So not, and you can clearly see so distinct particles or
So something
So this would be like larger particles that like can easily come out of solution.
yeah, or you can like kind of clearly see like oil and vinegar, right? So they're not miscible. So you can try to shake them, but then they're going to separate into two distinct regions again.
So I think the example that was used in the book was gold, like panning for gold for this one. Because you have all the dirt, then you have the gold, then you have whatever else is in there. That would be the heterogeneous, right?
Yeah. So kind of maybe thinking to sand sifting as well. So I'll go right like sand sifting, gold panning. Just where you're trying to separate a big rock mixture, so maybe you have big pebbles versus really smaller grains, and if you want to separate that out, you have to use a physical means. And again, you can separate out your heterogeneous mixture. Oh, soup is on the chat, so soup is a good one, right? Especially like chunky chicken. Or
Does this relate to like density of the molecules of the substance? So like one density is gonna be heavier that goes to the bottom and kind of separates?
it could. So like, we'll put that idea of density, but it's also solubility and miscibility. But yeah, all those different ideas, right? How are they going to separate? So, right, are they miscible or not? So that's kind of the first question, right? Can they mix? Is it soluble? So that's always a trick to get things pure. You can add water to something that'll drive salts into the water layer with like an organic, so you can wash the organic, it's called. And so that's like a separation technique. Yes, you can use like density that could, help with separations. Again, it just depends like what you're trying to go where. Yeah.
But a lot of substances dissolve in water. Are there any substances that dissolve in a gas?
Yeah. I mean, so I would say actually like it depends what you mean by substances dissolve in water, because like if we're talking about organic compounds, they don't dissolve in water, so they dissolve in organic solvents. So yeah, that's actually a whole challenge of chemistry. So like sometimes chemists are almost facing an existential crisis because an entire university can make like more chemical waste than the entire town, right? Just because of all the solvents use. They're not doing anything bad. That's just the nature of the beast. So there's a lot of research is like, how can we replace these organic solvents, which are potentially bad, with water? So anyways, gone off the rabbit hole again. And so then what would be a homogeneous mixture? Kind of what's the difference? You can also think of separation techniques.
Multiple compounds and maybe elements combined.
So still, yeah, multiple compounds. But then what's the key point with homogeneous? Or maybe an example is a good one. So yeah, evenly distributed. And then someone want to give us some examples? So paint, that's a good one. So paint, right, some mixture of organics and whatever the compounds they use to get the colorant and whatever else.
What about like coffee and milk?
So coffee is a good one. So coffee itself could be a mixture, right? You have just like caffeine and all those wonderful coffee flavors. And yeah, milk, and then Skylar, right? Soda is a good one, sort of evenly distributed. Holly.
So this isn't an example, but would you say that this type of mixture, like the different things that are in the mixture, have a similar polarity?
I mean, that's kind of why, but you probably don't want to get that far into like defining it that way. But yeah, that's kind of like why they would be homogeneous potentially, because they're all dissolving, and yeah, like dissolves like, polarity, but so kind of, maybe like Gatorade. Well, that's why you have electrolytes in water. They're all soluble. So put Gatorade. Other thoughts? Oh, we like soda, Dr. Pepper. I'll put Dr. Pepper. Yeah.
Say like unrefined oil. It's like a bunch of different types.
Oh, yeah. So it'd be a mixture of like hydrocarbons. So again, oil, hydrocarbon blend. Yeah.
Quartz or sand?
So, sorry, I have to think about that one, because quartz is mainly considered silicon dioxide. Yeah, so quartz would be a mixture. Since it's mainly uniform.
So it would fall under this category?
Yes, it'd be a mixture.
What about metal alloys like steel?
So those would be good examples of homogeneous mixtures, so metal alloys. Any other homogeneous mixtures that we like?
Titanium glass.
Titanium glass.
I actually had a question. Something like carbon fiber, would that be, is that a, what's the other one? Is that just carbon? Is that an allotrope or is that its own, is that a mix?
I think carbon fiber is a mix, because I don't think it's just carbon. It's some sort of like plastic thing. Yeah, because it's like a polymer, so that'd be more like a mixture. All right, other examples, questions? Oh, sorry, and then.
Maybe concrete?
So concrete could be a tricky one, because it kind of depends, like, you know, sometimes you see that concrete and it's super, super smooth and maybe you even slip on it. So that might be a good example of like a homogeneous mixture. But then if you have kind of more rocky concrete with big pebbles in it, then you're talking about like a heterogeneous mixture. And, you know, so on an exam, like if you ever get confused by that, like, you know, I don't know how to make this judgment call, you know, just make your explanation like, oh, I'm putting concrete as homogeneous because I'm thinking of really smooth concrete. And so, right, I'll put that, so like concrete, we'll say smooth, and then versus, right, concrete with rocks, big pebbles. So yeah, it kind of depends. Kind of like with cheese, right? Like we could do cheddar cheese, that's more of a homogeneous mixture. Jalapeno cheese is heterogeneous, right? Or, you know, Swiss cheese with the big holes, that would also be heterogeneous. Oh, yeah.
Would glue be a one?
Yeah, so glue would be a good homogeneous mixture. So a lot of future formulations chemists in here, hopefully. And so again, right, this is kind of relating back, how are we going to separate them? So with something that's a homogeneous mixture, maybe you would need to do a distillation.
Use magnetism.
What?
Magnetism in some cases.
I mean, maybe. That's a very specific scenario. But yeah, like more distillations are used a lot.
Like a centrifuge.
Yeah, so centrifuge, again, not the most common chemistry technique, though. And so here is just from your book, so I stole this graphic, but I, of course, wanted to point out the huge safety violation. I have no idea why they're distilling with an open flame, so you would not do that. So please don't ever distill with an open flame. That's how you start a huge fire.
Why is that?
So, right, whatever you're distilling, it's not shown here, but there's a joint in the glassware there, so then your substance will start coming out, and then next thing you know, with this open flame, your entire apparatus would be engulfed in fire, and that'd be a lot of fun. So, yeah, so don't use an open flame, so that's why heating mantles are invented. And so those are nice, electric, right? They stay at a constant temperature, so you can actually distill. And then, of course, right, the idea is whatever boils off first comes off, and then, of course, it rises up here, and we have our condenser with our water jacket to cool everything on the inside, so then it's nice and clean. And so we'll do distillation in lab. And then, of course, there's tons of other techniques to separate, which, again, you'll kind of get a flavor of as we go on. And so I'll just kind of go list them, right? There's like mass spectroscopy. You can look at compounds, characterize them. TLC or chromatography. Have you guys ever done like the chromatography with markers and stuff in school? You don't do things in school?
Like
No?
the stuff, like coloring on paper and then dunking them in water to see them run, yeah.
Yeah, or because you're supposed to see like what colors are in the different markers. Yeah, so kind of the same idea. So we'll do some chromatography in here. But right, same thing, just so you can separate inks out. That's how they separate compounds. So they have giant columns and can separate their wonderful organic compound. And hopefully, so right, we can use IR, NMR, and my plan is hopefully to set up a tour with SOU so you could actually look at an NMR. So when I like say these things, it's not just something magical and mysterious. All right, so let me pull up homework over here. Because in your book, so I love your book, but it's also kind of dense, and sometimes it doesn't always make that much sense. Sorry, give me a second here. And so let's look at your book, actually, and just kind of see what it is. So it just kind of mentions this AMU part really quickly. And so I feel like we should kind of go over this more and talk about it since it does pop up in your homework. And so, right, it's saying, well, we have this atomic mass unit, and so it's just kind of this arbitrarily defined unit. And so we have to get to how it's defined. And so we have, right, they've set our atomic mass to 12.01. And so blah, 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 right? It talks about kind of this ratio thing. And so let's kind of dive into not what your book is saying, but really what is the mass on the periodic table, what does it come from, and kind of what are isotopes, because you need that knowledge for your homework. And so let's start with carbon, actually. Oh, I forgot we can't zoom in on this. And so does anybody know what an isotope is? Let's start with that. So yeah.
An isotope is a chemical element with a certain number of protons. So we have multiple isotopes of hydrogen and uranium.
Right, certain number of what though?
Neutrons.
Yeah, different number of neutrons, right? And so, and I apologize for this because this is just kind of like the nature of the course, how your book is set up, and the homework and everything. So it might feel like we're jumping around, but I promise you that I'm not, and just ask questions if you're completely confused over here. And so basically we have, right, our periodic table here. It's arranged. And so we said, well, carbon, we have these isotopes. So maybe let's even back up another step. So we need to say, well, what the heck is in an atom? And again, it's just kind of the nature of the approach. So it's kind of like an atoms of first approach. And so the way the course is set up is like, oh, we're going to go back and like look at an atom later and look at all this waves and lights, but we didn't really stop and define what an element is. So we have our atom, and right, we briefly mentioned that it has neutrons, protons, and electrons. They just kind of gloss over this in our introduction here. And so neutrons and protons are in the nucleus of the atom, which is, of course, right, the center. And it's also where all the mass is. And so that's kind of the colloquial term, is that, right, the mass of an individual atom, so mass of individual atom, is equal to, right, our neutrons. And so this is basically the number of neutrons plus our number of protons. And so then our electrons and our protons, so we should, again, just clarify. So protons, so everyone is on the same page, are formally positive, and electrons are formally negative, but they are equal and opposite in charge. So that's right and important. And so then we have to kind of talk about isotopes a little bit. And so we had said, well, isotopes are basically atoms with different numbers of neutrons. And so these different number of neutrons, of course, gives us different masses. And
Just give us different reactivities as well, or like less stability maybe, or more stability?
reactivity, like stability is more the thing. So that gets into more like, you know, how radioactive it is. So basically, right, something that is carbon-13 and something that is carbon-12 will really react the same way. So again, not to get too far down the rabbit hole, but you can do like mechanistic studies using carbon-13 labeled things because again, they react the same. But yeah, some of them, so let's talk about our carbon isotopes. So we have carbon-12, carbon-13, and carbon-14. And so what do you know about carbon-14 though, thinking about stability?
It's used to date fossil records to see how old they are because the half-life of like so many million years.
Not a million years, but about 5,000, I want to say 7, I don't know, something like that. But definitely 5,000 years, something on that order for its half-life. But yes, so that's the key point, is that it's radioactive. Yeah.
How, I know that isotopes are really commonly found in nature. How did they come to exist? Like we have a carbon atom and then it loses a neutron?
Oh, well, that's a great question, right? So that's like the thing that we don't necessarily know, and so it depends on the isotope, and so some of it can go into like what was the original abundance, right, during the Big Bang, and that's how some things were formed, right? Some of these can be made through nuclear reactions, and so yeah, at some point, we're not really sure why it happened, but you know, there exists some proportion of carbon-14 atoms, right, that have, again, the extra neutrons.
I think I know the answer to this question, but I'm asking anyways. Are there a good number of elements that are actually more commonly found in their isotope form as opposed to like their pure form?
I mean, so that doesn't make sense what you said, because they're always going to be in some isotopic abundance. So, yeah, maybe we can, you can rephrase the question if that's not what you were asking. But let's get into now the AMU and kind of what your book was getting into, but they said it so esoterically that I understand it went over everybody's head. And so kind of, oops, we got to look at a periodic table. And so now the question that we want to answer is, well, why is carbon 12.011 on the periodic table, right? And so kind of the standard and why we have this AMU and why it's defined as what it's defined as is that we wanted to set a standard, basically. So we wanted to say, hey, well, I want carbon-12. I want that to weigh 12 AMUs, basically. And then I also want 1 mole of that, which we'll get into, right, to equal to 12 grams per mole. So that was pretty key. So, okay, now we've set this mass. But then the next question that you might be asking yourself on here is, well, how it doesn't match 12. Well, that's due to our isotopic abundance. So to get our true average mass on the periodic table, and for the purposes of our lecture, I'm kind of just using rounded values. But if you're doing this, right, to do it, perfectly, to set your standards, you have to get, right, your exact weight in AMU and then multiply it by the known isotopic abundance.
So it's slightly over 12 because there's other isotopes and less abundance.
Yep, and so how it is roughly is carbon-12 is about a 98.9% abundance, and then carbon-13 is the other, significant portion of that, so 1.1%. And then carbon-14 is really small, so I think it's 1 part per trillion. So negligible, but yes, averaging those masses up then gives us the mass on the periodic table. And so let's actually do this with bromine, because bromine is a little more fun, and I like making a point about bromine. And so bromine,
Why is bromine and mercury blue on this table?
because they are liquids. Yeah, so different, that's the beauty of these periodic tables. Different periodic tables have different information. So this one makes a point to tell you the state that it's in. Again, that's going to be in its elemental form, because you probably want to know how you're going to have to work with it. And again, we'll keep revisiting that idea, right? We got to know how they act, what they look like, how they react, so that we know how they behave. All right, so let's take a look at bromine. So again, you can always look this up for yourself, right? So this is kind of what it means to look at isotopes of something. And so again, kind of orient yourself. Well, these are obviously synthetic isotopes that have been made at some point. You could delve into the literature over how or when they were observed. But then what I care about is these 2 stable isotopes of bromine. So we have bromine 79 and bromine 81 in about a 1-to-1 ratio. And so that is, again, the ratio that they would be found in.
Can you go back to that?
Oh, sorry. And so that gave me a second to pull up this bromine. So this is called a bromine mass spec. And so now we're starting, now if I can find it, sorry. And so a mass spec just basically shoots the molecules, and then you can get the masses. Obviously, if you're watching CSI, it also shoots out exactly what the name brand product is, so not real. But we can compare our isotopes, and so this is what we're kind of saying in the abundance that were found. So maybe going back to your questions, are they found like this? So yes, right? If I have a compound that contains 1 bromine, roughly 50% of those bromines are going to weigh 79, and roughly 50% of them are going to weigh 81. So that's what we want to glean from that. And so going back again to the mass found on the periodic table, and again, I'm just going to take these rough numbers for bromine. So kind of our rough average atomic mass.
Is there any reliable way to separate different isotopes of the same atom?
That's not my area of expertise, yeah. So I don't know how they make isotopes and stuff like that. So, so we take 79 bromines, so let me just rewrite this information. So we have it, so a 50.6% abundance versus bromine 81. And so again, this won't quite match the periodic table because I'm just taking the rough estimates of our mass. And So now we can plug it in, so 79, and then of course converting our percent, so times 50.6 or 0.506 plus 81 times our decimal form, so 0.494. And so that gives us, right, our average mass of about 79.9, which is probably roughly what's on our periodic table. Oops. Sorry, too many windows. So yeah, 79.9, and like I said, we're a little off since we just used some pretty rough numbers, so. All right, so that kind of explains that, and then we can look at your homework, and so that's where this comes in. And in addition to isotopes, we also have ions, so let's again cover that so we're all on the same page. So what are ions?
Additional electrons.
So it could be additional electrons, but could be fewer, right? So I'll say a charged, could be an atom too, could be a molecule that we'll look at, right? We'll look at polyatomic molecules. So it's charged. So if it is positive, right, it is lost an electron. Because again, right, we said we define electrons as formerly being negative. So if something is positive, it is lost an electron. If something is negative, has gained an electron. And the other key point we should remember is our number of protons equals our electrons for a neutral molecule. And so I like to write our formula as our charge. I don't know why I wrote 0. So charge is equal to, and I say protons plus electrons, but I always multiply my electrons by a negative sign, right, because they're negative. So if you needed to do protons minus electrons to have that formula make more sense to you, do that. But I don't know, for my brain, I need to like add them because electrons are always negative. But. So now we can look at your homework and look at, so let's try B if you haven't already. So just take a minute or two, kind of go through that in your head. So how many protons, how many neutrons, how many electrons? So now looking at this, so how many protons do we have? So 6, right? And so again, just to be super clear, so your protons is also your atomic number, right? So whatever nice number is there, okay, that's my number of protons. It defines what the atom is. So we can always look back at the periodic table. And so now for B, how many neutrons would it have? So 8, right, 14 minus 6, because this is our mass now of that atom that we're looking at, that isotope. And so again, right, that's how we identify our isotopes, by the mass. And so now it has a little plus sign, so saying we lost electrons. So how many electrons do we have? So 5.
Will there be a little number up there if it's lost more? Can it lose more than one electron first? And
Yeah.
if it does, will there be a number like 2 plus or?
Yeah, so if it had a 2 plus charge on it, it would have a 2 there. So yeah, or you could, lose 3, 4, 5,
Oh,
6.
I see over there on the sulfur, there's a little 2 minus.
Yeah, so let's look at that example now. So looking at F, so take, again, a minute or two. So watch what information is given, our little 2 negative up there. Try to zoom in.
Question 2, are we doing that by volume, or are we doing it by number of molecules?
This one you do it by mass. So sulfur, what do we get for protons? It's 32 sulfur. So 16. So it is a number here, right? So this is also the atomic number. But again, right, maybe you feel better just double checking yourself. So 16. And so then how many neutrons do we have? So 16, right, just taking 32 minus 16. And then we had 2 minus signs, so do we gain or lose electrons? So gain, so how many electrons? 18, excellent. All right, other questions on kind of this portion right here? All right, let's take a little break. So maybe let's try to be back by 12:10 or so. And then we'll continue on with our law of definite proportions.
Some of my homework done. I don't have the second one done completely, but I have all that done in my abstract. I was
Yeah.
wondering what you had that case of like electrons. No, sorry.
Oh, the molecule
Yeah,
kit?
the molecule case. I'm sorry. Can I take a picture of it? I was trying to find
Oh,
it on
yeah.
Amazon and I couldn't figure it out.
The baby one I just posted online, a link to. Oh, I think.
Oh,
Yeah, there
do you think
it
it'd
is.
be better if I get the big one if I'm taking OChem and biochem next?
It depends. So I actually don't like the big one for like OChem and biochem. This would be good for OChem, biochem, and maybe even like more expensive kits that have more things.
So, quick question.
Mm-hmm.
When is the homework and the labs due?
I mean, whenever. You're stressing me out more about the dates, right? Just whenever you get it done. Ideally this week.
Okay. Cool.
Yeah.
So I did some of it, not all of it.
Yeah, so I'd rather you take the time to do it.
I have one more thing. I won't be here October 31st. I'll be out of the state. Can I come to the Tuesday lab that week instead of the Thursday lab?
Yeah, that would work.
Okay, thank you.
I was having a little trouble, when you're ready.
Yeah, keep talking.
I was having trouble accessing that journal article that you had referenced for the lab one.
Did you go through the steps outlined? Because you got to go through the RCC website, library guides,
No.
chemistry. So yeah, try
I
it.
just went through the Blackboard link to that website, and then I was trying to get through there, and that wasn't turning anything up. Is there instructions on the Blackboard to access
It's not
it?
on Blackboard, but it was on the lecture video, because I went over it last week, so then you can watch the previous lectures.
Okay, all right.
Yeah,
Okay, and that,
But,
and
yeah,
you
if
show
you-
how to get.
yeah, if you email me, I can send you a direct link.
Okay, all right. I'll take a look at the lecture too. Thank you.
I actually had the same question. I said I did get access to the article, but I was just wondering if that's like the primary place where you can be reading our journal articles.
Yeah,
stuff like
and if
that.
it's not a JChem Ed one, I'll have to make it available, because
Okay.
that's the only journal that we pay for from RCC.
Okay. All right.
Yeah.
Thank you.
This is gonna be a silly question, but the protons is what makes an element different, right?
Yeah.
So carbon is 6, 7 is, I don't know what the next one is.
Yeah, exactly,
Okay, so
nitrogen,
okay.
yeah.
Okay, perfect.
I finished this lab and I emailed you the abstract. I don't know like how we're supposed to like turn that in or whatever, but
Yeah, I prefer paper copies,
Okay.
but I can print it out and staple it to your thing, so yeah, just make sure your name's on it.
yeah.
And then I prefer if you email me directly rather than going through Blackboard.
Okay, gotcha.
Are the due dates on the Blackboard correct for the handed homeworks?
No.
They're
I mean,
labeled for the.
I don't know, like, so due dates are more to keep us on track for the course rather than a punitive thing.
Gotcha, okay. Because they're labeled as Thursday and I wasn't sure.
Yeah, so that's my intention, is to try to label them as Thursday, yes.
Okay, cool.
So I just like get the student, you'll print it off, or like should I print off the abstract?
I mean, if you can print out the abstract, that's ideal, but since you emailed it to me, I can print it out for you this time.
That works, yeah.
Okay, yes.
Is
you
the
can.
printers in like the library?
I believe they have printers in there for access for y'all, but I may need to check on that. Thanks.
question for you. So I said reactivity, and you said it was more stability for the isotopes. What about the ions? Would that be more reactivity? Like if it has extra or
Yeah,
less
so that would
electrons?
probably be more reactivity,
Okay.
yeah. But, yeah, that'll also tell us like what happened, yeah. So that's related to reactivity.
Perfect, thank you.
All right, did we all make it back from break? All right, so then your book starts to get into really the history of chemistry and kind of how we got to where we are, which even, I mean, your book doesn't give a full extensive history either, so. And so, again, big picture ideas that we want to understand is, of course, right, we have a chemical reaction and matter is neither created nor destroyed. So it is just rearranged, right? So we can say a chemical reaction is just a rearrangement of atoms. And so again, right, when we kind of study this, especially looking back at the past, right, it seems very obvious to us. We're like, oh yeah, obviously, right, they're atoms, they can be rearranged. Yeah, we know this discretely. But obviously it was not that simple. Yeah.
In the case of like a nuclear fission reaction, is there a loss of mass during that?
So yes, it's related to the energy, but let's hold that thought for way later, because we're not talking about that. And so with, right, a chemical reaction, you of course want to define, again, what you're reacting. And so I always like this reaction just because of the beauty of it, right? You take sodium metal, so obviously, right, you can't eat that. And then we combine it with chlorine gas, again, also highly toxic. And you can make table salt. And again, we're getting to this, but kind of in our chemical reactions, right, it tells us the state of the matter. So solid for our sodium, again, what it is elementally, how you're reacting it, and then some sort of amount. So these are given in grams, which is not typically what we look at, but here we're just looking at the conservation of mass is what we're being emphasized. So right, we didn't lose any mass, we just combined our 7.7 grams of sodium with our 11.9 grams of chlorine. And so that was a lot of kind of the early experiments, right? They're trying to figure out, well, what's what, or, you know, is mass conserved? So that was kind of one of the first things that they're trying to tease out with all these combustion experiments. So, okay, so that was kind of, you know, again, one of the first ideas that they figured out that, again, the total mass of these substances does not change, but still didn't understand that we have small indestructible particles. And so it just kind of jumps here in our notes, right, that we had Joseph Proust came up with this law of definite proportions, but we should probably, again, back up a little bit, because a lot of these experiments also involved a lot of other people as well. So we had Joseph Priestley, who was doing some work with gases. So I think he was working on finding kind of oxygen gas, so he separated it from mercuric oxide. And again, these were kind of early experiments, and they weren't quite sure, you know, what these gases are. They also had kind of this weird theory of like, you know, maybe oxygen is this flammable substance of life, but again, they weren't sure, like, they weren't making the distinction between compounds and mixtures of gases, basically. So that was kind of difficult. And so we also don't want to forget about Lavoisier. So he also did a lot of work on this. So let's put in here Lavoisier, a French chemist. And so again, similar sort of thing. He did a lot of work to kind of work with these gases and air, so kind of repeating these experiments. And so kind of the first step that they're trying to understand is kind of, you know, are they atoms? Are they molecules? And so this is where we got to this law of definite proportions. And so basically they were saying that no matter how small of our sample, that we can prove that it is the same as kind of natural elements. So that was pretty revolutionary, right? So he proved this with our, by making, copper carbonate, copper. So he proved that with copper carbonate. But again, it's important to remember, right, again, at this time, everyone's kind of doing these different experiments. They're debating back and forth, trying to define, you know, what are all these gases. And so let's at least do some math here with this. And so basically, again, how this kind of broke down back in the day. And this is a good example because back in the day, they had a hard time distinguishing between CO2 and CO. So just imagine, right, they're just trying to think of them as completely distinct compounds and not made up of different ratios of carbon and oxygen. So this was very puzzling. But let's look at how they might analyze this. So they have 2 samples of carbon dioxide, and so you can decompose them into their elements. So they say one sample produces 25.6 grams of oxygen and 9.6 grams of carbon, and the other produces 21.6 grams of oxygen and 8.1 grams of carbon. So think about how you can set that up, right? What does it want you to calculate? How can you show that they have the same proportions?
Divide oxygen by carbon within both, and if the proportions remain the same, you have the same molecule.
So you said divide the ratios of oxygen to carbon.
Yeah, you take 25.6 and divide it by, is that 9.50?
9.60, yeah.
9.60. And then concurrently you divide 21.6 grams of oxygen with 8.30 grams of carbon. And those should give you the same result.
So that's one method. So let's look at that. So just punching it in to follow. So 25.6 divided by 9.6. So we get 2.66 for that one. And so 21.6 divided by 8.1. And so again, 2.66. All right, so that's one way to prove it. And so what's another way to show that they're consistent? So the hints there, what does this mean, mass percent? Yeah, so percent of total mass. So we just have to do that. So we can do, again, for sample 1 here. So right, our percent mass is going to be part over whole roughly. So then, right, doing the math for that. So we can take 25.6 grams over the total. So 25.6 plus 9.6. And so just keep your parentheses straight for this one if you punch it all in. So that gives us, right, sig figs, so 3 sig figs, so 72.7% oxygen. So that'd be another way to define it. And then let's repeat that, see if it's consistent. So then sample 2. So repeat. So now 21.6 on top, and then the sum of our total masses on bottom. So again, now just punching it in my calculator. And so we get the same percentage, so those are really close, really spot on, so right, 72.7% again. So does that kind of make sense? And again, right at the time, this would have been confusing to them, because then they would have argued about this, because they're trying to figure out what ratio carbon and oxygen combine. And right, so like we know there's CO and CO2, but they didn't know that. So again, there's kind of arguing about this and kind of unsure. Again, since they didn't know about atoms and elements and everything like we do now. And so Dalton kind of started teasing out, though, the fact that there were atoms and maybe things aren't always in these ratios, right? So we can't always say that carbon and oxygen are in, right, a 2.66 ratio. And so he's saying, well, maybe there's, right, atoms and they can define in different proportions as long as, again, kind of they're whole numbers. And, right, we'll put in parentheses, so marching closer to atoms. So again, easy for us to kind of judge their confusion. But now, so Dalton's kind of teased out that we have elements that maybe can combine in different ratios. Again, especially with oxygen, so using our oxygen experiments, we can make different compounds. And so right now we know this. So we could have, right, CO, CO2, obviously N, nitrogen and oxygen make a bunch of different combinations. So etc. So that's what all we're saying. So now they can combine in, again, these kind of whole number ratios. And so that is our key. So getting to our formula, right, there's still some sort of indivisible unit, which is, again, kind of the key point of Dalton, that Dalton still recognized, right, there's still some little particle. I'm not sure if they quite had, again, atom really defined at this point, but yes, there's an indivisible substance. And it's not just, right, like a mixture of things, because that was, of course, again, the debate. And so with that, so right here's our multiple proportions. So now we're saying, okay, now we can explain this big mystery between carbon dioxide and carbon monoxide that was troubling all these early scientists. And so yes, right, we can have them where it combines in a 1 to 2.6 ratio, or if we have one atom of carbon for one oxygen, then we have a 1.33 ratio. That just corresponds to the mass. And so then, right, just the ratio of these masses to itself is, of course, our whole number. And so this is just, again, defining our subatomic particles. I think we kind of went over this earlier. But again, here's our AMU mass. So what a proton is defined as, neutron is defined as, and then this is why we say our electron mass is negligible. So 0.00055 AMU. So again, that's why it's negligible. And then there's our charges. And then we'll come back to this at some point, but here is our coulomb. So, right, 1 electron is 1.96 times 10 to the negative 19 coulombs. And so we want to just start to, again, understand how we represent them. Same information, just different pictures, right? This is more a space-filling model. So our chlorine, right, is large and trying to show all the space being filled. Here is kind of showing, again, our bonds and our shape, but not really showing kind of how many. So that kind of information is lost here. So just connectivity. And then a black is always carbon, right? Our halogens are typically green. Oxygen, right, is always red. Nitrogen is typically blue. And then phosphorus can be yellow, just like sulfur. They tend to use the same colors. Sometimes you have this different orange, but don't usually see that. And so we'll get to, again, this eventually as we go through the course, right? So how do you determine the shape? So, right, you probably don't know that just looking at that. I don't expect you to at this point. So that's, right, a skill that we'll be working on. So let's start getting into naming our compounds, right? So that's kind of the next step is, well, what are we working with, right? And how do we name it? So we have our ionic compounds. And so our ionic compounds can be kind of divided into two rough categories. So metals that only form one type of ion, and of course metals that form more than one type. So, sorry, looking for my periodic table. Oh, let me grab it. And so first we should kind of identify, well, what metals fall into those categories. And so let's kind of highlight metals that are what we call monovalent. And so typically, right, these group 1 and 2 metals over here. And then let's highlight some other ones. So zinc is typically 2+. And so if you're looking at your periodic table, this is where those little numbers can kind of start to help you. So you notice those little charges. And so to me, it feels like we've kind of jumped around again for a second, but just bear with, again, the course.
What are the highlighted metals as a property? What are they highlighted to represent?
So we're getting there. You gotta let me get through it, right? So we're highlighting, and so again, this is what I was saying. It probably feels like we have jumped, but that's just the nature of the course. So if you notice, we have kind of this group 1 here. They all have this +1 charge. And so right now, just kind of accept that. We can quickly say, yes, they have 1 valence electron. They're all water reactive. That's why they act like that. But again, right, we're just trying to define that these will only lose 1 electron. We're going to, again, delve into the nitty-gritty as we continue. And then our next one that's highlighted, so our group 2, our alkaline earth. So these are kind of more reactive with acids, and so now, right, they're 1, 2 over, so they tend to lose 2 electrons. So again, just accept it for now, right? A big 2+, that's what they tend to do. So then going back to these things, you know, a lot of people kind of have questions of like, well, what do we typically see, blah, blah, blah. And so for these, we would see like calcium, you know, 44 2 plus. And right, it's always going to be calcium 2 plus because that's its pattern to lose 2 electrons. We'll get into the s orbitals and all that detail as we continue though. And so again, right now, just mark other ones, just kind of appreciating and writing it down. We'll get into the why as we continue. So aluminum, typically 3 plus, so again, highlight that. So these are our monovalent ones. Oh, and silver is typically considered as 1 plus, but it can take other states. All right. So then going back to our rules here. So, okay, the metals that only form one type of ion. So, right, we define them. So we said that was typically group 1 and group 2 metals. And then the other ones. So to name them, how we name our one type of ion, it's pretty simple. So we just name our metal and then change the ending to "ide." So again, if you've taken chemistry before, I'm sure you're familiar with this. If not, right, that's why we're going over it. We're all on the same page. So KCl would be potassium chloride, right? So you're just changing the chlorine to chloride there. So calcium oxide, again, right, look at our periodic table. Okay, calcium is under my 2 plus category. And so I know it's our monovalent metal, and then again, change our oxygen to oxide. Other things to start thinking about kind of with this naming is notice, right, the formula. So this calcium oxide, there's 1 calcium to every 1 oxygen. And so again, we can start to piece out why. And so again, look at your little periodic table. So notice your halogens. So what little charge do all your halogens have? Minus, so just -1, right? So they're all -1. Again, we're getting into the why. We'll learn that these all have 7 valence electrons, right? It's actually listed right here, 7. So that's corresponding to our 7 valence electrons. So they're 1 away to a full octet. Again, I'm kind of throwing out words at you. We'll revisit what that means. And so again, they typically tend to be in this -1 oxidation state, meaning they're typically accepting those electrons. So now if we go over to oxygen, so these all have a big -2 on them. So now they're 2 away from our octet. And so they tend to gain 2. And so that's how we know how to write them. So, right, we can look, well, calcium is 2 plus, oxygen is 2 minus. Those charges balance out, so they're in a 1-to-1 ratio there. So let's try to name another one. So now what would this one be called? So write it out. You can shout it out later. Looking at the chat too. So magnesium fluoride. And so you don't want to add any prefixes in front of it, right? Because our charges dictate the formula. So we just say magnesium fluoride. And then, right, we could derive back out the formula. So magnesium is a 2 plus charge, fluorine is -1, and then you can do what's called this swap trick, which is basically just the math shortcut. So quickest way to solve a 2-variable problem is to swap the variables. So there's our magnesium fluoride back out.
Why is it not a difluoride? Same way you have like carbon dioxide.
So that's for covalent compound naming. So with the ionic compounds, right, it's again dictated by the charges. So with the covalent, what you know, what you're getting at is they can be in different ratios. So like we were saying with the NO, right? They could be 1 to 1, 2 to 1, 1 to 2. So yeah, hold that thought on the covalent compounds. So does that make sense for naming our ionic ones, at least kind of our basic ones? So the charges balance out. We can get our formula back out.
What is type 1 cation?
Oh, so that just means, again, ones that only have one valence oxidation state. So going back right to our group 1, group 2. So you're never going to have like calcium 1 plus, right? That just does not happen. So that's all that's meaning. So then going to our, right, kind of type 2 compound. So now our second type is going to be our multivalent metals. And so all this means is they can take different oxidation states. And of course, this is typically, right, your transition metals. And then we'll note a few of those intertransition P block metals as well. And so all your transition metals. And so again, right, there's a lot of oxidation states on this periodic table, but it's not meant to be an exhaustive list. It's just kind of the most common ones, especially for those transition metals. And obviously, right, in research, you can do all sorts of funky states. So basically, right, all these are right, are multivalent metals. So the lanthanides and actinides are not as exciting as you might think. They do have different oxidation states. But yeah, so you would probably, again, indicate its oxidation state with the Roman numerals. And then so other ones that you need to indicate. And so your periodic table does kind of help you with the P block one. So you can see thallium. So it has a +3, +1 on your table. And then highlight lead. So that is a 4 and a 2. Polonium would also be one. And then tin is another common one. And I mean, you could probably throw antimony and tellurium in there, but we don't do too many compounds with them. And so now let's look at how we name them. And so now the tricky part, and again, the key point, well, they're multivalent metals, so we have to indicate their oxidation state by some method. And so that's, oops, I didn't put our notes there. So that's what we do for this one. So now my multivalent. So now we use Roman numerals to indicate the oxidation state. And so our oxidation state, again, refers to kind of how many electrons it has gained or lost, again, compared to our base. So kind of related to number of oxygens, but not directly. And so let's look at, let's say we were trying to then write the name of our formula. So let's say we have this compound. So we have this iron chloride compound. And so now we have to back out and find the oxidation state first of our metal. So basing it off of the known one. And so we can examine this. Okay, I have iron and chlorine. And again, I can go back to my periodic table. Well, iron could have different oxidation states, so I can't use that. But I know my chlorine is always -1. So that's our piece of information that we need. And so if chlorine is -1 and there are 3 of them, what's my oxidation state of iron? So positive 3, and so now that we know the oxidation state, we can name it properly. And so now we can just say iron 3 chloride.
How did you determine it was, have the 3 ions that it was positive charge?
So I based it off of the chlorine, and so that's kind of the rules for these things, is you have to base it off of the other elements. And so looking at our halogens, so they're always -1. So then you go back, so -1 times 3 gives us -3. And then we need an overall charge of 0, right? Because if there's no charge indicated, then you assume it's 0. So that leaves iron as 3+. Does that make sense for that one?
So, is it just based off of like what you do the balance, like, but is it just like a balance thing, is that why it's iron 3?
Yeah. Yeah, because it's based off of the chlorine, so, yeah.
What's the name of the group right before the noble gases?
The halogens. Yeah, so we have our halogens. And so let's try another one. So see if you can name this one versus, oops, that compound. And so for starters, we have to know what oxygen's typical oxidation state is. So what did you determine that to be? Yeah.
I got iron 2 oxide.
Oh, hang on. You jumped ahead though. So what do we find the oxidation state of oxygen was though? So -2, right? That's just, we're accepting it for now from our periodic table. And so now we go back, so they're in a 1-to-1 ratio. So I think you said it, so that's how you determine it was iron 2. And so now we can write our formula. So this would be iron 2 with our Roman numerals, and then oxide.
Is that just rust? Iron 2 oxide? Or is that?
I think iron 3 oxide is rust. So then this next one, which I kind of gave away, but now we can do what I like to call our reverse swap trick. And so what you can do to kind of test it out is, well, just reverse it. And then when you reverse it, see if it matches what it's supposed to be. And so what I mean by this is, okay, well, we back out the 2, and -2 is indeed, right, what the oxidation state of oxygen is. So now that works out, so that means this is 3. So now we have iron 3 oxide. Yeah.
Is there such thing as iron 4 oxide?
I'm not sure, but I would say probably, or someone's at least attempted to make it. Sorry, I lost my train of thought for a second. Oh, one point I wanted to make where the reverse swap trick lets us down. So try this one. See if you can determine the name for it. You have an answer for this one?
I got tin dioxide first.
Well, remember, we don't use the dis and tris, so you said tin 4 oxide, correct? So that's good. So tin 4 oxide. And so you didn't get tricked, but let's go over how we might have gotten tricked and just kind of what to watch out for. And so in the chat, just make sure you're putting the Roman numeral on that tin oxide, since there's, well, 2 forms of tin oxide. So this one, right, is again tin 4 oxide. But I wanted to point out, so if you did what I call the reverse swap trick, and we backed it out, you would get 2 plus and 1 minus. But then, what's kind of your red flag here?
Oxygen's fine in terms of like it's
Not that it's diatomic, but what does this number mean again? Well, it's its oxidation state, which is related to the valence electrons. But then, so what's the problem?
It's how many electrons it needs before it is following the octet rule and its valence is full. So in this case, that's saying, oh, oxygens only need 1 electron to be full. But if we go back to the periodic table, they don't. They need 2.
So it needs 2. So then, once we recognize that, okay, just know I need to multiply everything by a factor of 2 then, and now we get, right, the tin 4 oxide with that. So I just wanted to show, right, we can use reverse swap trick, just watch it and check it, yeah.
So I guess that's my question is, looking at the previous example, the swap trick worked, and this one it doesn't, so basically the way to know if that is the proper method to use is just to double check your periodic table.
Yep, and so, right, just do that check, like, is oxygen, does it have a -1 oxidation state? And then we go, oh, it doesn't, but then we just multiply everything by our appropriate factor, and yeah, then we can use that. All right, other thoughts? Yeah.
How does the math behind this swap trick work again?
So all I'm doing is setting up, right, it's basically a 2-variable problem because you have your oxidation state, right, of your metal times how many, so like your number of it, plus your oxidation state of your nonmetal times how many. So, right, this is basically X, and this is Y. So then you end up with kind of like this 2-variable problem, but then you might know, the metal oxidation state or something. So that's all I'm doing mathematically. Any other last-minute thoughts, questions?
One more question. What about something like sodium hydroxide, which means NaOH?
Sodium hydroxide, so NaOH.
Yeah. That one.
So sodium hydroxide is getting into polyatomic, so we'll hold that thought for later, so just the last second. You would have to know that this is a polyatomic, which again is coming, so that corresponds to hydroxide. But again, yeah, getting ahead of ourselves there. So be sure to talk to me, again, especially if you're feeling overwhelmed. I'm not trying to go too fast, but it's just the nature of chemistry. You end up kind of reaching for a lot of ideas right away just to kind of get to basic concepts. But just, again, hang with it. We'll keep going through our compounds, and then we'll start getting into stoichiometry. All right, so thanks for everybody for being online, and I will go ahead and stop this.